Now we're going to study a new logical operator. It's my personal favorite logical operator, and it's called the conditional. So the conditional operator, which we usually write with a right pointing arrow, it's a binary logical operator. So that means it has two arguments, p and q. And the way we usually pronounce this logical operator is p implies q, or if p, then q. Like every logical operator, it has a truth table. And let's go ahead and look at this truth table that this logical operator has. So we have two inputs, P and Q. P implies Q is true if both P and Q are true. If P is true, but Q is false, then P implies Q is false. If P is false but Q is true, then P implies Q is true. And if P is false and Q is false, P implies Q is true. So this is the definition of this logical operator. To see a little example in English here, suppose that P is the proposition I did math today, and Q is the proposition I thought hard today, then P implies Q is the proposition if I did math today, then I thought hard today. So the if then structure, if P, then Q. If I did math today, then I thought hard today. Now, an important and kind of counterintuitive aspect is that this implication, this conditional operator, it's actually true in some scenarios we might not expect. So specifically, these bottom scenarios, when P is false. If P is false, it does not matter at all what the truth value of Q is. So this is called vacuously true statements. So here's the key idea. If P is false, then the statement P implies Q is always true, no matter the truth value of Q. So this can lead to some surprising kinds of vacuously true statements. So for example, if unicorns exist, so I'm going to assume that's a false statement, sadly. If unicorns exist, then discrete math is not fun. So everyone knows discrete math is fun, but unicorns don't exist, unfortunately. The first part, sometimes called the antecedent of that implication, is false. From a false antecedent, no matter what the consequent, the second part of the implication, no matter what that is, the result is always true. So this is called vacuous truth. If P is false, then P implies Q is always true, no matter what Q is. The logical implication operator has an important and useful alternative form. So, to discover this alternative form, let's complete another truth table. What I'm going to do is I'm going to do the truth table for the expression not P or Q. I populated the inputs P and Q, so let's go ahead and jump right in. If P is true, then not P is false. If P is false, then not P is true. Then, not P or Q, so if either of not P or Q is true, then not P or Q is true. So The important thing to notice here is that this is exactly the same truth table as the expression P implies Q. So the big fact that we have proven here with our truth tables is that P implies Q is logically equivalent to not P or Q. Let's see an example of using this to simplify a logical expression. So I'm going to start up here with not P implies Q. So not parentheses P implies Q. What I'd like to do is simplify this as far as I can. So I'm going to follow standard form, which means I'm going to take this step by step and justify each of the steps that I make. So the first thing I'm going to do is I'm going to use this equivalence that we just discovered. So I'm going to replace the implication with not P or Q. So I'm just going to call this equivalent form. And I'm going to put a little star there, and I'm going to put a little star right here so that you know that's what I'm talking about. I'm using the equivalent form that we just discovered. Now, I'm going to use De Morgan's law. So I'm going to pass this negation symbol through the or inside the parentheses. So I'm going to obtain not P and not Q. So my justification here is De Morgan's. Now I can keep going. I have two negations in a row. I can cancel them out using the double negation property. And I'm going to call it done here. So by using this equivalent form of the implication operator or the conditional operator, I can express the conditional in terms of more familiar operators like negations and disjunctions, so not and or, and I can use that expression in order to simplify logical expressions involving conditionals. If I have a conditional statement like P implies Q, then there's a few other kinds of statements that are related and which we often study or care about in practice. These are the converse, inverse, and contrapositive. So combined with an original conditional, there's kind of four logical expressions that go together as a set. So if my original expression is P implies Q, the converse of that expression is Q implies P. So I just swap the locations of P and Q. The inverse of this expression is not P implies not Q. So in the inverse, I leave the P and Q where they are, but I add some negation signs. Then in the contrapositive, I add negations and I swap. Not Q implies not P. So these are four different expressions that we can obtain by doing different kinds of transformations to the original conditional P implies Q. Now, the important thing to understand about these expressions is that they are not all logically equivalent. Not all of these are logically equivalent to each other. In particular, and you can show this using truth tables, P implies Q is logically equivalent to not Q implies not P. And this is the contrapositive. So the original is logically equivalent to the contrapositive. Furthermore, it's also the case that Q implies P is equivalent to not P implies not Q. So this is the converse, and this is the inverse. So the converse and inverse are also logically equivalent. But the original, I'll label that here as well. The original, that one is not logically equivalent to the converse or the inverse. It's logically equivalent to the contrapositive, but the converse and inverse are equivalent to each other. Let's take a look at a little English example here. So if P is the statement that I did math today, and Q is the expression the statement that I thought hard today, P implies Q says, if I did math today, then I thought hard today. The contrapositive, not Q, implies not P. It's a pretty sloppy P there. If I didn't think hard today, then I did not do math today. That would be my contrapositive, and this statement is logically equivalent to the original statement P implies Q. If I did math today, then I thought hard today. So from a conditional statement, P implies Q, I can also form many other kinds of conditional statements, the converse, the inverse, and the contrapositive. I can replace the original with the logically equivalent contrapositive anytime I want to, but I can't replace it with the converse and the inverse. Those are logically equivalent to each other, but not to the original statement. There is one more logical operator for us to introduce, and that's the biconditional. We saw last time that the converse of a conditional statement, of an implication, is not logically equivalent to the original. However, sometimes the converse just happens to be correct, it's true. So what happens when both a conditional statement and its converse are true? Here's an example. Let P be the statement that I got better at math, and let Q be the statement that I practiced math. So on the one hand, if we look at P implies Q, if I got better, I practiced. So this is true. The way to get better at math is to practice math. So if you got better, it's because you practiced. But also Q implies P. If I practiced, I got better. So that's also true. If you practice, then you get better. That's what happens when you practice, is you get better at math. So this is a case in which both the original implication P implies Q and the converse Q implies P are true logical statements. And these are not logically equivalent. They could be false if P and Q are different, but in this case, these implications are both correct. And we have a special definition for that. This is the biconditional. So the biconditional operator, which is written as one arrow pointing in both directions, left and right, is defined by a logical equivalence where we say, okay, P is biconditional to Q, also pronounced P if and only if Q. So the only if part is new, P if and only if Q. It's defined by this logical equivalence. P implies Q, we can think of that as the original conditional, and Q implies P. That's the converse. When both of these are true, then we have a biconditional. So in our case, we would say I got better at math biconditional if and only if I practiced math. So, again, it's not always the case that P implies Q and Q implies P are true because they're not logically equivalent. But sometimes they are both true. Both of these implications, P implies Q and Q implies P. In that case, we have satisfied this right-hand side, and that's the definition of the biconditional operator. We can also define the biconditional with a truth table. Every logical operator can be defined by a truth table, and this one is no exception. And you'll do that on an upcoming warm-up problem.